Hi everyone. So just before we quick start, I'd rather go the deep dive. Just want to know if you have heard of Vespa.AI, not the scooter company. Just to clarify, yeah. Oh, there's one person. That's actually a great start. So anyway, Vespa.AI was spun off 3 years ago from Yahoo. They've been in Yahoo for 10 plus years. They are the backend for Yahoo Finance and now Perplexities, Spotify. So essentially, it's an enterprise scale retrieval solution. In the RAG world, it's called a vector database, but Vespa's more a tensor database, which means you can store multi-vectors, which is embeddings, dense embeddings, sparse embeddings, metadata, all in the same row, and do fast query all of them at the same time for doing precision retrieval. So today, what we're going to talk about is related to that. I'm just going to give like a 5 to 6 minute overview of, I don't know, probably there are a few enterprise companies here, explaining how the GenAI apps are built and the scaling problem we have. Because just as a background, I've been in the life science and tech for 20 years. My last stint was at Snowflake, before that AWS. And a lot of the conversations in the last 2 years was about like building a RAG chatbot. That seemed to be the biggest pet project everybody had before now the agent took over, and now everybody wants to build an agent for anything like this on. And a lot of the RAG chatbot I have, what I've seen of the scaling problem, they start off with a great MVP, and when you want to actually productionize it and scale it up, there are issues. So just a quick resetting or orienting you around what the RAG problem is and what the context-based retrieval is all about. Now is about scaling. The second thing that I've seen is that, at least in the industry I work with, everybody can solve for text, but when it's multimodal or when it's in a complex PDF that has a chart, that's a PowerPoint, or in my world, it could be medical images, there's a problem. It just doesn't scale well for multimodal data. Third is precision of response. I think somebody had a question even earlier, like how do you understand the user intent, right? It's great when you ask an exact prompt and it can find the information that's in the prompt. But sometimes your user intent is not very clear. So how do you find the precise document or the precise image when there are unset patterns, right? And that's what we call the relevancy tuning and precision, and how you can adjust for that during your retrieval function. Radu will deep dive a lot on that. It's a very important use case for e-commerce. And the last is long reasoning agents. Great segue from the last session where you talked about, okay, how do you know that this is the product that the user wanted to buy, for example? When you have multiple agents that are being chained, the precision retrieval from the first step can amplify. If it's not accurate, downstream retrieval can be hampered. So this is one of the reasons why when you design the RAG systems, the retrieval is extremely important, especially when you have long reasoning agents that are reasoning over multiple workflows. So these are the 4 problems that industries are looking to solve for, besides the first excitement of, hey, I can now query some text that I couldn't query before, or create a chart that I couldn't create before without IT. So this is what the modular architecture is oriented towards, right? And I frame this not around textual, structured data, because honestly, text to SQL and structured data is a bit more simpler. But today, when we look at unstructured corpus, which is probably what's not tapped well, we have the documents. The LLM race is kind of stabilized. There's a lot of state-of-the-art models that can do embedding, so nobody's creating fine-tuned models as much. Most of the models out there can figure out the information from the text pretty easily for embedding. What's important for industry is to create what we call the institutional knowledge base or a context knowledge base. So what becomes key is your context that you create over your institutional data. And then you can have LLMs for summarization and do interactions. So today's session would be about what is that context knowledge base all about? How do you store them as tensors or multi-vectors? And how can you take advantage of retrieval functions to ensure you get precise retrieval from this context? So in this way, you're decoupling the data from the model from your context. And the models can change. So you could have DeepSeek today, Llama tomorrow, and it doesn't matter. You can actually change the embedding functions and the summarization functions. So again, the 4 paradigm is multimodal handling, which maps to storing them as multi-vectors. Precision retrieval, which is more on the end stage, is how do you relevance tune it? What are the parameters you can adjust so that you can tweak your response to what the user intent is, whether set or unset. Third is enterprise fitment. Everybody wants to work with one of the CSPs. The other problem we have seen is, okay, how do I operate in a vacuum? Like, no, you have to fit with a cloud provider or with the enterprise systems that you already have invested in. The last is cost efficiency. Very key. You can't burn up GPUs in just creating a RAG chatbot. Most of the, at least not the tech-first companies, have a cost constraint on how much IT budgets they would get. So when you do the ranking, retrieval, tensorization, again, I think Radu is going to deep dive on some optimization you can do in retrieval that can save a lot of crunching. Like if you have billions of documents that you have stored as a vector or a tensor, there are retrieval-specific filters you can apply to make sure you're not searching all billion at the same time for that exact word. So that's what we cover. And then some fun questions, right? If we do all of this, what do we want to do? We're not going to ask for a very simple, hey, give me what the sales forecast is for the next year. I think that's a very simple drag problem. We want to get something like this. In a life science, what set of patients show some kind of disease progression similar to an image? So we want to be able to search across a very specific medical term and in visual prompt and be able to get responses from your context knowledge base quickly with reasonable cost. So that's the aim of building these solutions. In an e-commerce world, you can think of, hey, I want to buy a red shoe. And then you want to find similar red shoes that are available in your e-commerce store. How do you do that fast in a very less cost performance, in a performing manner with less cost? That's the whole idea of this ecosystem. So today we have a couple of demos as well to bring this to life. The first one that I'm going to show is complex PDF, and it's not a show and tell, so it's just to show you it can work. A bunch of PDFs which has got images, charts, graphs. We used a late interaction and vision language model called ColdPally. It's open source. It's in GitHub. There's another one called ColdQuent. What it does nicely is that a lot of effort, data engineering effort, generally is spent on chunking. Right? You have to pre-decide how are you going to chunk the document so that your retrieval accuracy is very good. In this case, the late interaction model can actually treat each of it as an image, create multiple patches and overlapping patches, and embed each patch as a dense embedding. And then you can also embed the text next to it in a tensor store. And so basically what you get is multiple billions of pages or billions of rows of tensors, each tensor having embedding multiple patches of a page along with metadata and the text function. So when I do a retrieval and ask, hey, give me a couple of interesting questions, in this case, I want to know what's the business objective or tell me what's inside this graph or percentage. It can actually not only retrieve the right document, but also highlight in a heat map where in the document it found that information. So important if you're looking for attribution and lack of avoiding hallucination and proof. With that, this is what we did. In this case, we took medical and clinical documents. As we said, used ColdPally, a late interaction model, dubbed it into Vespa, and then created a very simple UI to interact with Vespa. So what's important here is to know that the tensor is basically a bunch of information that contains all of the document metadata, which is who wrote it, what they wrote, title, etc. Dense embedding of the document per patch, and the text chunk for the page so that we can use a hybrid search. We can also do a text search, and we can also do a semantic search, so it increases the relevancy. Sometimes the semantic is approximate. The text is kind of exact. Sometimes you need a combination of both to weight the answer better. And doing retrieval, we exactly do that. You do an exact match. You can do an exact match if you really think that, in some cases, for me, the disease name has to be an exact match. I don't want machine learning to approximate it. So I can configure that. I can do a hybrid, say 50-50. And then additionally, filters can be applied to say, okay, all of these documents are great, but I want only to apply the filter for the disease first so that I don't have to get any other responses that are not interesting. And then we get those images. Let's see if this works. Which in a session like this.
Wait. This is a demo. This is your demo, right?
Open, cool.
Okay.
Oh, so this is just a static page, and we already have some predefined questions. So, and again, since it's life sciences, there's a bunch of medical information here. So let's ask this one, say, mechanism of action for trizeptide. For people not familiar from the US world, trizeptide is a Lilly drug for weight loss, which everybody is now attributing. So as you can see, in like less than 0.10 seconds.
Minimize that.
Okay, cool. So in less than 0.0 seconds, it scanned through the bunch of documents we had loaded, and the information that we need is actually inside this page. It retrieves the top 3 from the relevant document where trizeptide was the medication, which is kind of not a GLP-1, but similar, that acts on you for obesity reduction. Finds information even from the graph, and then we use a simple Gemini flash to summarize, to say how does trizeptide work in the body? Essentially, the mechanism of action is just another word of saying how does it work, right? And we can go to and ask another question as well. Let's say MACE production. Okay, let's ask this one. This is interesting. So here I'm comparing 2 drugs. One is from Novo Nordisk, semaglutide and trizeptide, and I'm saying is there a weight loss percentage for patients with again, it finds information across different documents. There is one document that was a study on that weight loss comparison. There is a poster from another setting where they had the comparison number really attributed, and a table that has cost comparison. But it is able to retrieve that and then summarize exactly the answer. So the idea is you want to leave is think of documents, especially complex documents, as tensors, and then you can do fine-tuning during retrieval, and that will help you give you more precision, and also be able to attribute it exactly to the page or the references, especially in a regulated industry like this. With that, I'm going to hand it to Raju to get into some of the semantics of how this works.
Yep. No pressure.
At least the demo works.
Yeah, I mean, you got that going. Yeah, so I'll try to dive. I'm not sure how deep. I'll ask some questions just to know like what you're interested in as we go along. By the way, I saw some of you taking pictures. Go ahead. It's just that these slides will be shared, I think, on a Discord or something. So I think everyone will have them. And there are lots of links in here that you can use to resource like sample apps, blog posts, all that. Like they're dotted around everywhere. So I just want to start with the basics of how semantic search works, as it's kind of usually defined in the industry. I assume probably most of you will know this, but there are lots of embedder models out there that can embed text. So you can throw your document text in there and it will generate a dense vector. You can throw the query at the same model and we generate a dense vector. And then you can compare the vector from the query to the vector from documents and give you the closest ones. And the naive approach is you just scan all the documents, see who's closer, and you're done. Of course, this doesn't scale. So most retrieval engines, and Vespa is no exception, have some sort of way to make it faster. And as there's no free lunch, it will have some trade-off. Usually it's approximate search. So Vespa will use HNSW, comes from hierarchical navigable small world. The idea is this is a small world. You can go in 2 hops from here to here, and it's hierarchical because it has multiple layers. Think of it like zooming in a map. So you can go to what seems to be the closest and go to the next level and so on, then you find closest vectors. There are no guarantees, unfortunately, with regards to quality. So you might miss something essential. You don't really know. But it works in practice. It tends to work pretty well, but you need to measure for yourself. So this works well for the typical vector search, like one embedding per document. We have an embedding for the query. It also works well, in Vespa at least, if you chunk documents. So think of, for example, a Wikipedia page. It can contain a lot of info. So we chunk it, and then each chunk will have its own slightly different significance in different embedding. And then you can throw that to HNSW and you can search. And effectively, you will get back documents that have the most relevant chunks. And of course, there's nothing that prevents you from combining the chunk level scores to the document level scores, and you can do all that. And I'll kind of scratch the surface of combining these things. But basically, it's possible. And we have a really nice, I won't point all the links from the slides, but this one's, I think, particularly important. We have something called the RAG blueprint. So a lot of the techniques that we think are best practice for RAG are crammed in there. So yeah, have a look. And then I think we're getting closer to what Harini was demoing with late interaction. So this is when you can have multiple vectors on both the query side and the and the document side. So this was, how many of you have heard of Colbert? Okay, so some of you. So this late interaction was introduced in Retrieval with Colbert, and the point is we generate one vector for each word. So if you're looking at text, we're generating one vector for each word, and we do the same for the document and for the query. So the late interaction part is when we do the query, we take every vector from the query itself, and we look at the document and find what's the most similar word, and just loop through all of them and sum all those scores up. So presumably, the most relevant document will have the most, the higher score. This is usually more accurate than previous methods. The downside is it can only be brute force. That's the late interaction part. You cannot use the HMSW. So usually you would use this late interaction as a re-ranker, and I'll go over that as well. and this is really kind of what Hagni was showing. So there are models like Colpali that where you can take a page from the PDF, and with Colpali it will divide it into patches, like 32 by 32. So you have 128 patches in an image, and then you do. That's going. Each patch will have its own vector, and then you do late interaction on that. So basically, you don't need OCR. You just query the pages because both text and images can live in the same vector space, and that's how what you've seen earlier works. Like you ask the question, and that's going to generate a bunch of vectors, and then the pages were already scanned and vectorized and all that, so the query. So this is what I had regarding dense vectors, but I think it's also interesting to look at sparse vectors. So with dense vectors, dimensions are implicit. So it's like you don't know how the model created these. What does the first dimension of a vector mean? It could be color, it could be whatever, right? But it could be useful. It's not necessarily a competition here. It's just it could be useful to have explicit dimensions, right? Like effectively a color or whatever, especially when the user, coming back to the questions about intent, when the user asks a question, you can reduce some dimensions. And the use case I will go with here is searching for secondhand cars. You have dimensions like price, like miles per gallon, like age of the car, whatever that the user might be interested in. And you can encode that in a tensor. So here's one example where basically we take features like miles per gallon and price, and we normalize them and put them in a tensor. So it's effectively, a map. That you just would just index in Vespa. And at query time, you do the same. You ask for the user intent, either explicitly or implicitly. We will do this implicitly with an LLM. Like I would say, give me a cheap and reliable car, which tends to compete, right? Like a reliable car usually is not cheap. So it will try to figure out, okay, how much does each thing matter? And it will build another tensor. So now we can simply do a dot product between the tensor of the query, the user's intent, and what is encoded in the documents, right? So we do similarity much in the same way that we've done with dense vectors. So this is how a rank profile will look in Vespa for that. So really quick demo, again, because we don't want to abuse the time, but this is totally vibe coded, the UI, so don't judge. But it's an e-commerce app where you have the usual facets. So let's say, and you can use them for filtering, and I guess you could add a search box to do actual filtering for things that are really, hard criteria, right? Like let's say I really want a manual transmission car, right? I really need to use both my legs. That's non-negotiable. But maybe other things can compete and can, I can have some leeway. So let me go with I want a cheap and reliable car. Internet doesn't cooperate really well, so it might not actually work. But what it does is, this is chatbot, right? It asks GPT-4 or something, hey, this is what the user asked. These are the potential dimensions. You have makes, you have models, you have whatever. Build that preferences tensor format, and there's just a JSON, right, that will add to the query. So in this case, it figured out that cheap probably means price, and reliable probably means age and mileage. And even then asks me, do you have any specific brands? And I can say, I don't know nothing about cars. Let's say I want reliable brands. And again, we can leverage the knowledge of the LLM, and you will probably come up with some brands that are known to be reliable. And I can adjust the, I mean, this is a UI UX thing, which I know nothing about, but I would assume you out that maybe you want Honda, Subaru, and Toyota, that kind of thing. So this is sparse tensor. So that, and this sample I put just to do this product, like that's it. But usually in a production environment, you would add other dimensions. So it could be dimensions coming from the documents themselves, right? So let's say the cars have a location. Where is the seller, right? I can compute the distance between me and the seller, and I can inject that into the score. I can, if I actually run a query with some text in it, I could take the score of that query and add that in as well. So now we have a hybrid search between the preferences I have, the sparse tensor, and the actual, let's say, lexical search or vector search that we've seen earlier. One thing that I will add here is that, again, normalize everything. So the BM25 score, which is, how many of you have heard of BM25? It's quite a few. So BM25 score is not, is unbounded. Like you can have scores like 0.2 and you can have scores like 25, and it doesn't say much about how relevant the document is to your query in itself. It just matters if it's more or less than another document score. Right, so you want to normalize this, and using an arctangent is one way of doing it. And then you typically also add some weights. So this is a weight that you can change at query time, and then you can embed that into the score itself. So you can say, does that matter more or less compared to, let's say, the user preferences or whatever dimensions I have. But those weights don't have to be static. You can have a model, you can train your own model that would probably infer things like, oh, wait, if the price is really good, then I don't really care how far the car is, or things like that, right? Depending on your use case, you can train your model and you can make that work in that relevance formula. Though usually models, I mean, so far we talked about ranking documents in the sense of ranking all the documents in my code. So it could be billions, right? And so if we do this on billions of documents, we don't want to have a very expensive expression. So if it's a more expensive model, then we typically use it as a re-ranker. So with Vespa, this works that in a way that the retrieval phase. So when we do the vector search and we ask for the top 100 or 1,000 or whatever documents, that's a filter in itself. Or if I say transmission manual, that's another filter in itself. So only documents that match my filters will be ranked, and that's the first phase ranking that goes to all these documents that match, which again could be millions. So it needs to be cheap. But we can say get the top N, and most search engines will have that. Vespa is no exception. Get the top N of those matching documents and re-rank them using something more expensive. And with Vespa, that's another cool thing that you can do it with the data. So on the node that contain the data, and you can also do it again if you need it when the stateless nodes will merge data from all the data nodes. That's when you can do a global page re-ranking. So again, hit the total top N and re-rank them, and there you can also use a GPU to make them all run faster. Now I'll get to a bit of more boring thing, which is lexical search. I would argue that lexical search, you can think of it also as a sparse vector retrieval problem. So effectively, each word that you're looking for can be thought of as a dimension. And then both documents and queries live in this n-dimensional space where n is the total number of unique words in your index, right? So if I have 2 dimensions here, brown and fox, I can have a document that just contains fox, and I have a query brown fox, and like how close are those vectors to each other? And then what we really care about is how do we compute, those vectors, right? How we compute vectors themselves and also the similarity. And there are a number of formulas here, and BM25 is the most popular. And I'm just going, because I saw quite a lot of you don't know what BM25 is, I'm just going to explain the basics of it. There are many other formulas that work around the same dimensions, they just have different formulas. So let's say I search for the phone, right? Those 2 words, the or phone. I don't care which one matches. So dimensions, there are 3 dimensions BM25 cares about. One of them is term frequency. If the term appears more times, the document is going to be more relevant. The other one is term rarity. So presumably, phone is rarer than the in my corpus, so it carries more weight. It's more specific. And then it's field length. If a field is longer, then it's just going to be by accident more likely to contain my documents. And then Vespa also comes up with something called native rank, which adds 2 more dimensions on top of those. One is first occurrence. So if terms occur earlier, they tend to be more relevant. And then proximity. If terms are closer to each other, they tend to be more relevant. But the point is, with Vespa, and if you use any other retrieval engine, you would typically be able to pull out these dimensions, either tune the existing behavior. So for example, BM25 has some tunables that you can change. Vespa allows you to do that. Or you can take individual dimensions like how early the term occurs in the document and inject that into your own custom ranking formula. So these are, I think, the kind of broad capabilities that might help with all this. So I'm just going to kind of wrap it up. So when building a retrieval sort of implementation, I would first look at what dimensions are relevant for my use case, right? Could be lexical search, could be the dense vectors that we talked about, which come in many, many flavors with different trade-offs. We can look at sparse vectors, which you typically use to encode user preferences, but there may be other applications as well. And you can look at document attributes, right? What is, maybe popularity or whatever ratings may be in there that might be relevant. Normalize all those before combining them, because otherwise, it's likely that something will completely dominate the score, and we don't want that. In Vespa, use tensor math wherever it's possible. That's because it's much, much faster. Like how I did it with the cars demo, it's very fast to compute a dot product between 2 sparse tensors. It's much faster than I could take the same data and put it like as raw fields. And in the rank profile, I can say, yeah, take the price and take the age and multiply them and do whatever. But that would be much slower, because then for each document, you would have to go to the attribute store, fetch the data. And that's not only specific to Vespa, that's for everything. Let's say you're using Elasticsearch or something. If you write your own script with your own custom ranking function and reference those fields, it has to fetch them, combine them. It's going to be much slower than dot product between 2 vectors. So use tensor math wherever possible. If you can define your problem in terms of tensor math, that's rank profiles also expose a lot of math that you can use, but I would see this as more as duct tape, right? So you pull those dimensions in the rank profile, then you combine them, normalizing them, you add them up or whatever you need to do. Rank profiles allow you to do a lot of things, like you can define functions, you can expose, you can, when you return results, you can say, hey, this little bit of the rank profile return 3, so maybe that is or it isn't what you expect when you're tuning it. Or you can put rank profiles in different files, you can inherit them, so it's kind of like a programming language, if you will. And then lastly, you can train re-rankers to re-rank your top n. And typically to do that, you'll need judgment lists. So judgment list is basically, hey, here's a query, here's the documents that I'm expecting. And if you have a lot of those, you can use them to train. To first measure if you're actually making progress, right? Because you may be doing fancy things and you're actually worse than the M25. This is not uncommon. And secondly, if you want to train something, you can divide into the training test and all that jazz. And you can use getting judgment lists used to be a pain in the behind, but nowadays you can use LLMs to do it. There's a link to a blog post there. You can tell the LLM, generate some queries, run queries, and figure out which documents are relevant and which are not. So with that, if you have any questions for us. Yes.
So I'm exactly building this RAG pipeline for my product. How do you well? So we obviously got different way vectors, sparse, vector, and all of those stuff. What evals do you use to actually judge which one is more effective? Because all of them, so sure, they can give me an answer, but over like 1 million documents, like how do I know which one is actually working well? Sure, I can only judge like 100 of them.
That's a very, very good question. So first of all, how do you evaluate? Which metric do you want to use? Because that's, I think, a big question. And I'm trying to answer your question more generally so that it benefits everybody or most. So which metric do you care about, right? Because if you do RAG, like in your case, then I think precision is very, very important. You don't want to give junk to the LLM because it's just going to hallucinate. But maybe if you have a human that's doing e-commerce search, then maybe you care a bit more about recall, just to show the right products, even if they're maybe a little bit below. So picking the right metric, I think, is important. And then there was another side. The question again. Sorry, I lost my train of thought.
Multiple vectors like dense sparse.
Yeah, I said you can't evaluate everything. So yeah, that's it. When you create the judgment list, the problem is you cannot take all the queries and judge all the one. Let's say you have 1 million documents, which is not very many, but then you have to evaluate 1 million documents for every query, which is never going to happen. So what people usually do is you take different retrieval methods. So you take, let's say, lexical and vector search separately. Maybe you have some other ways. And let's say to the user, you normally give back the top 10, you get the top 100, and then you evaluate them. And then you're going to get a higher chance of evaluating what you would look at. And I think what I would also do is when I would evaluate, I would check if the documents are evaluated against that query already. Because the metric that is most frequently used, which is called NDCG, normalized discounted cumulative gain, that is often used in e-commerce, that has this blind spot that if I didn't evaluate a document, it gets 0. So effectively, a document that I haven't seen before, which might be relevant to my query, will count as if it's completely irrelevant, which in effect means that if when I'm tuning an existing system that I've already evaluated, it's extremely unlikely that I'm ever going to get better, because most likely I will get documents that weren't already in my result set and they will have a 0 because they weren't evaluated. So I would reevaluate and make sure they're evaluated.
Are you using different embeddings for the same documents, for example?
Yeah.
So one of the things that we actually wouldn't show is that there are different like when you're doing retrieval, you can say semantic or hybrid or just BM25. So the only way we saw that for life science is I tried the toggle option. Like in this case, widget 3, suppose you did a custom ranking figure. The only way to solve for this is I actually type the question and see which one of those my test cases, when does BM25 work better, when does the hybrid work better, when does the semantic only work better. And that really depends upon, honestly, unless I do some customization, it honestly depends upon how particular I want. For example, my brand name on the drug is important. I want BM25 on that, because it should be exact match, but everything else can be approximate. So I need to try that out, and then hopefully, like in the use case of Spotify and others, they actually analyze it over time and create their own custom language function. In which case you can write a weighted formula that says this 0.5, that 0.6. But that's try and run in the toggle. Yeah.
Just thinking about when you started this presentation, it became highest knowledge base. So in this example, let's say a million, and the email is different. So is there any way to, for example, raise up the knowledge marks out of the document and use this part of the evaluation, because then your knowledge mark will perhaps has the enterprise knowledge, but of course can't capture everything. So somehow you capture the most important, then because just the enterprise, for example, article XC, for example, in coding, you have, this person, take and achieve for primary points, and you different code base, and you have this. How do you link these documents with the actual, class and all these? So you use both vector search and also, knowledge graph to cross-check against each other.
Sorry,
So are you
I
saying-
saw you were nodding, so
No,
I
I
was
got
just
into
assuming
this.
you got it. Now it's your problem.
Okay. I can LLM summarize it. And my LLM might not be that accurate. No, so what I'm saying is that when we talked about the enterprise knowledge base,
Yes.
you're saying that we have millions of documents. How do you benchmark? Or you want to create a benchmark set of accuracy for responses? And are you saying, I lost you in the knowledge graph part. Are you asking if you should create
So
one?
can you create knowledge graph to basically capture the knowledge? Because then you have different ways to measure the accuracy of the query, for example. And you know whether your retrieval is accurate. Have different ways to measure.
So your accuracy can, suppose you have a bunch of documents and you have a bunch of test conditions, say this is the accuracy for this set of questions, this is the accuracy for this set of questions. Will the knowledge
So like
graph
the-
help to?
Can I
Will you create knowledge graph?
categorize questions in different sort of buckets
And then we have
and
different
use them for what? For
retrieval accuracy.
So the knowledge graph basically capture the relationship
right?
of different entities.
Yes.
or-
Mhm.
And so that it will be a lot more accurate, perhaps. And sometimes vector search, it really depends on different way of vector search. Now, I'm just asking, because accuracy of knowledge graph that you can basically cross-check. So, for example, that it reduces your chance of hallucination, and also documents. Embedding the weakness is about the context window. So your chunking strategy is also hard.
Yeah.
So
Problem
just self thinking, how do you deal with this? Do you utilize knowledge graph as a reference for things like that?
Some of the graph rag applications that I've
Rag
seen,
graph.
graph rag is for reducing hallucination, but it's very difficult to create a graph. And before even GenAI, there's been graph and license model targeting, extremely difficult to build and maintain. So it's always been a start and start project. So the only thing that the graph rag examples we have seen is you dynamically build a graph at the run, basically to say, okay, these are the top 20 or 100 set of questions. Would you create a graph that links the more accurate terminologies or words or the responses into a relationship, and you ask the graph rag first to benchmark the answer before asking the LLM to summarize. But in an enterprise scale like this, where it's billions, it's very difficult to keep that knowledge graph up and running for all answers. So the best example of graph rag is when, say for example, in this medicine terms, right? I have say 10,000 set of medical terms that are important. I load them into a graph and I also load all the related terms. So when I do the search, before I do the retrieval, I would get the graph to get all the related terms and search across all of it and use that for filtering just so that I don't miss an important document. But there is very controlled set of graphs. The other user at Toku, they ask the question and then they build the graph dynamically by interpreting what two words are related. And when they build this graph, it remains for the purpose of querying and then they shut it down. Big knowledge graphs, I have not seen it being successful, at least in the industry. I'm not sure about others.
You're welcome.
Well, it's actually interesting. Let's say you had the same medical journal, but like an oncoradiologist would have a different embedding viewpoint on that than a traditional radiologist versus someone in another medical field. How can you take that context-aware embedding on and then apply that? That's something that you guys.
That's an extremely very good question. So the important thing in the three-modular architecture is an embedding model, right? So for more stuff, this example used the cold Pali, which was pretty decently context aware. Like even when I asked a question about MACE, which I didn't show you, which actually in the medical world, it stands for major adverse cardiovascular events, right? Even though it's a general purpose English model, it was able to interpret that and find it in a graph. But when I go to the more advanced examples like medical imaging, which I can store as a tensor, we've done another example where you can actually find cancer cells. You need to fine tune the embedding model. That becomes extremely critical key. So if you have an oncologist who's working very special, say in spinal or cervical cancer, better take Kopali and fine tune on his dossier. The context knowledge base is exactly that. It's going to be contextually aware depending upon what you're embedding. So I would recommend fine tuning, but for these corpuses, must have.
I'm not clear on what the advantage is of using a tensor database over a vector database for this particular algorithm, because Kopali creates embeddings as vectors and it's super fast doing that. So you mentioned something about adding like metadata to the documents as well. So you're saying you would have some labeled data as well, and then use that and create tensors. I'm not clear how you would ingest the documents as tensors, and then what the advantages of using that as a database. So could you just clarify that, please?
Yeah, and just to preface the fact that I'm not an expert in any of the other vector databases out there. I come from the world of, let's say, search, Elasticsearch, Solr, and stuff like that. I've been working for more than a decade, but I don't know really how to compare Vespa, because I don't know the capability of, let's say, quadrants. So coming back to the rest of your question, yeah, I mean, you can embed the dense vectors, with Kopali and stuff like that, but then you can add other dimensions that may be interesting for you. So with tensors in particular, you can add also sparse tensors if you want to encode some explicit dimensions. I don't know how that would apply to this particular use case. Maybe something like cardiologist or whatever is looking at, and then they'll come from a different angle, and then maybe that'll be something interesting to label explicitly. And then you can also combine this with lexical search, which can be very advanced. I mean, in this case, we're doing only BM25, like this is hybrid search. So I think one of the value propositions of Vespa is the fact that it can do both lexical and vector search really, really well. And so you don't really need two data stores.
So actually, the multi-vector problem there is that so this page is broken down into multiple patches. So a tensor, essentially, if I consider it like an array, it's an array of vectors, right? So storing it as a tensor means and since I'm using Kopali, let's say this example. This page, say, I'm breaking down into 10,000 patches. Each patch is dense embedded. So I have, and each page is a tensor, which means I have all the 10,000 different dense embeddings in one row, along with the English language text of it, along with additional sparse tensor. If I want to say, I want to store user preferences as a sparse tensor, say I want to know which physician it is. He's a radiologist, the other person is a clinical oncologist. I have user profiles, I can add that as another sparse dimension, for example. Let's say. All of this is one row in a tensor map, right? So when I do the search, I'm doing this hybrid search option on that single row to retrieve what is the most relevant page. In a vector store, and I think Quadrant does multi-vector, I don't know how it works, but like in Pinecones or the other regular vector databases, you would actually store each embedding separately. And then most of this work is done post-processing. You would get all of the patches that, say, for example, I search for semantic similar, I will get all of the patches that are interesting for me. And then at the end of it, look at all the patches that come from the same page, aggregate, remove the page duplicates, and then send the response. So a lot of the thing is done post-processing and post-engineering because I'm not running them as a single formula. So the tensor map actually helps condense the search retrieval, which rather than duplicates later. Because you are then condensing the page into one, then doing the operation to eliminate what is sort of.
Yeah. I was a little bit, lost at some point. I did like, no, I did like, your presentation and everything. I understand it. The only thing is, I have a little bit of difficulty linking some of your presentation where you talk about different things, but unfortunately, I don't have the image to into the detail. But you talk about normalizing things.
Right.
Some way there.
Yeah.
For one, I would like to know how you normalize things. How do I know the right way of normalizing? So you have a formula there which is not straightforward, you know.
Right.
That's one thing. And the second thing, I want the link between that part of your presentation and this part, because I was a bit like, two different things.
Right. So when I talked about normalizing, I think in a bunch of places. I think this is one of them.
This one, you know, this formula, for example. How do I know the right formula for normalize whatever?
So yeah, there are different ways to normalize things. You can just put things on a logarithmic scale, for example, or you can, in this case, it took an arctangent of something that I don't really know because I didn't write it. But it seems to do the job. It's really down to how you want to normalize. It's like, let me give you a much simpler example. Like in this car preferences use case. Yeah, so I have features like price. Like in the case of a price, what I care about is if the car is cheaper, I want it to have a higher score. So, but I still want to normalize this, and by that I mean I want to include all of those. I want to include between a -1 and 1. So what I did was, for price in particular, I said, okay, let's have a ceiling, because at some point, secondhand cars are just batshit expensive, right? So I don't care. So let's say that cutoff point is at 100,000. So I'm just saying 100,000 minus the actual car price, yeah, and then divide that by whatever it would get into that range. That's kind of a naive way of doing it. But you can make it exponential, you can make it logarithmic. It depends on how you want the score to evolve with. See what I mean?
That's fine, yeah. Thank you. But then, okay, second question will be about what you were presenting. Is it the tuning part of Vespa?
So the Vespa is the database which handles all of this, the tensor and the retrieval and the ranking. That's Vespa.
It's inside.
Yes. So it's and the idea of what you present is the concept of what you can use to build an accurate pipeline, not just with Vespa. Anything that can in general, retrieval and ranking.
And finally, Vespa for a company, is it just for retrieval or?
No, it's like, as you said, it's a tensor.
Oh, yes, it is.
Yeah, you can retrieve if you store it. Yeah.
So you want to say more?
And storage as well.
Exactly. So basically, yeah. So when you say retrieval, because he comes from a search paradigm, you're obviously only retrieve. He's already assumed everything.
Where did you retrieve it from?
Exactly, because everything is just searched. But in a RAG world, yes, you have to get your unstructured corpus into a RAG pipeline. You need to get it into a vector database or a multi-vector database or tensor database. So that would be Vespa, and this runs on all the cloud. So basically, you spin up Vespa and then you dump them as tensor, and then do all the school ranking functions that we talked about, and then we can relevance retune your retrieval. For example, the backend of complexity is Vespa. So the reason if you use perplexity and you're searching, you're getting precise results. It's basically indexed all of the web and anything else that we don't know about into the Vespa indexes. So it's billions of index, and it has implicit user personalization. Means it understands what the user intent is, which is what they use for retrieval. So you could build something in that, but that's essentially what it is.
Thank you. But is it something that you sell, or how is it?
The company, yes. Today we are not selling, but yes, if you'd like to buy, you just go to Vespa.AI, then yeah.
Thank you.
And there is free instances you can run and play around with. But yeah, please do just chat with us offline after the session.
Yeah, one last question.
I'm touching this.
Sorry, can you speak a little louder? Yeah, judgment list. That's right. Doing what it should be. Am I moving forward or am I breaking stuff? That sort of thing. So I think that's the primary thing. And then the second one could be to train a model. Okay, if I have enough of those, I can just divide them into training and a testing validation something, and I can train, let's say, XGBoost model or something where I can take the dimensions I care about and mix them up. How do I generate these lists? Well, there are a bunch of ways. First of all, is to get everyone that complains about search to actually write down what you expect and just put in your database. And the other way is to use an LLM. So basically, you tell the LLM, here are my queries, or you can even tell the LLM to generate some queries that things would be appropriate, and then you can say, okay, run. You can make a script. I can give you a link to one. Basically, run the query, get the first end results using normally one use retrieval methods, and say, okay, let's rank these results. Again, the LLM would do that, and then that would generate judgments.
The first option, utilizing people, probably best one.
Usually it is, yeah. Even people can also be wrong, but typically, they're a bit more accurate. And you can do also first of all, they don't exclude each other, but you can take human judgments and feed them as examples to the LLM to kind of align the LLM to what humans would think would be relevant in that way.
Great, yeah. So thanks to Radu and our team for the that brings us to the end of the meetup today. Please do stay on because time to mingle and get more drinks. And just want to thank Netmind again today for hosting everyone. There'll be the QR code up again if you want to sign up and get free credits. But the speakers will be around if you have any other questions. Thank you.
Thank you.